Yeah. Okay. Hi, this is Bob Westervelt, and I'll be giving. We've had trouble connecting with Rick Keller in the Pacific, so I'll be giving pretty much the same talk, only from my uh, point of view. And first, I have to share the slides. You are muted. I didn't think I was muted. Unmute myself. Okay, you're right about. Hi, this is Bob Westervelt, and so I'll be giving the Friday talk. We've had problems connecting with Rick Keller. Okay, that looks like it's working. Actually, maybe for this purpose, I'll do it sitting down. Is that right? Well, actually, maybe not. I think I will do it sitting down. Because that's okay. And so, what we did, going back maybe 20 years or so, is that Mark Topinka, uh, looking at results like we heard last time, where people were looking at electron waves traveling through a two-slit diffraction experiment, uh, we're motivated to really try to visualize where the electron waves went as they were going through the two-dimensional electron cast. And first, Mark Erickson in my group built a low temperature scanning probe microscope from scratch. We didn't know how to do it. Mark is an amazing guy, and he made it work. And we got sort of the classical flow through a narrow aperture working. And since then, he's done great works at Minnesota and is an expert at using silicon germanium devices for quantum information experiments. And then Mark Topinka followed up, and then he rebuilt the microscope in such a way with more spatial resolution so it could actually image where electron waves go. And so that's what I'm going to talk about. And we spent, a couple of years getting that going, but all of a sudden it worked extremely well. And we had a very happy 2 weeks where we got both a science paper and a Nature paper coming out of that. And then Mark is such a nice guy that he was shocked. So much success so fast after much suffering before that. So it was good. So I'll tell you about how that works and some of. But when that first worked, then I contacted Rick Heller, who's a theorist who worries about how electron waves move around inside structures like that. Rick worked with Don Eigler earlier, and Don is the fellow who used to scan atomic force, a scanning tunneling microscope to spell IBM with atoms on a copper surface. You've probably seen pictures of that. And then he worked with Rick to actually look at electron waves moving inside those systems. And then that turned out to be extremely useful because Rick knew exactly what we were doing, and we talked a lot. So I'll describe how that works. And these are some pictures of some of how that worked. And the collaborators in my group, Mark Erickson, Mark Topinka, then later on Brian Leroy, who's at Arizona, Kathy Adala, who's at Mount Holyoke. Actually, she's remarkable. She's both the chair of the department, has a new building, and raised $3.5 million for a maker lab where so that women can see how stuff works. And then Jesse Verlitovsky. And there's an outline. The idea, I showed you a picture before, is in order, on Wednesday, we heard about electron waves traveling through a two-slit interferometer. And people were very much interested at the time, about 1995. They're like, really, where did they go? And we were drawing potential paths, with a pencil on a piece of paper. Don Eigler was actually able to do things with scanning tunneling microscope, but at this larger length scale of microns, there wasn't too much going on. And we decided to use a charged scan probe microscope tip, essentially an AFM tip that's conducting in order to bounce electron waves off of the tip. And this gives a picture here how that works. Let me just turn the microphone like this. But far out of the picture, we have an electric contact that's putting a current into a two-dimensional electron gas. Here it looks like a green lawn. And the electron waves, the wavelength or half the wavelength is shown by these fringes. And the picture is actually done by Rick Heller, and it's a quantum simulation of what's going on, so it's actually accurate. And then the quantum point contact here is just about a half a wavelength wide. And so the electrons get squeezed quantum mechanically to sort of a point here. And then they emerge on the other side. And we saw earlier that in that case, the conductance is 2e squared over h, quantum of conductance from the Landau relation. And the way we can image it is we have a charged tip that sits over the top, and it actually depletes a hole in the electron gas. And the electrons can't go in there because there's no electrons there. They bounce backward. And the amount that bounce backward then changes the conductance that we're measuring. And then by doing that, that change is proportional to how many electron waves are going first. The ones that go sideways, they don't matter, they say. But let me go through sort of a basic quantum device model. This is what we've been talking about in the past couple of weeks to make sure that everybody has it straight. And so what we're going to do is get sort of a ray tracing model of how electrons move through a two-dimensional electron gas. And in quantum mechanics, you know that you have sort of a duality. You can think about where the particles go. And if you're thinking about particles, then they follow paths. But then also the wave function is actually a wave. And so it has a wavelength, and it can interfere with itself if you go by multiple paths. And if we're designing a device, think like you're an electrical engineer of the future, and you want to make a quantum device, a way to do it would be draw rays like you would for a regular classical device. But since they're actually waves, interference matters. And so you have to keep track of wave interference too. And the way to do that is to take the path here. And then you plot the wave function along that path. And so then wavelength here is given by some number. In the experiments that we're using, it's a low density electron gas. So that wavelength, instead of being the size of an atom, is a really long number. In this case, it's about 400 angstroms. And so it's 400 atoms long. And so it's so big that you can actually image it in the experiment. So it's not like an atomic number. And so then momentum then is just equal to H over lambda. Or also as H bar minus the K vector. However, so any questions about the way that works? Good. There's another thing that can be confusing, and I said it, but it turns out to be very deep, but gives a very simple result. And so let me go through that again. And so I've been talking about the electrons as if it was just one electron moving through a vacuum. And it turns out that that's good. Now, why would that be good? Because in electron gas, it's actually degenerate gas with the Fermi energy. This is not art. Uh, Fermi energy that's positive, and so electrons are all crammed in right next to each other. And so that you have a picture, we go over here. And let's assume that the temperature is absolute zero. So there's everything is very cold. And so you get a picture in K space of the occupied state are totally filled up to the Fermi K vector, or the Fermi energy. And you have a density that's equal to n. So the way it works is all of these states are filled and everything else is empty. But this is not doing anything, it's just sitting like function. And so then the question is, what happens if you put an electric field that's pushing force, which is the charge times electric field, that's pushing to the right? And the trick that makes everything simple is suppose that you look at electron state that's deep down inside this Fermi disk. Do these electrons move? Now you can answer the question. When you put electric field on or not? Extra chocolate for the, oh, pass the chocolates around. If you answer a question, you get extra. What do you think? So all these states, it's like the parking lot at Logan. You're trying to catch a plane, but all the slots are filled. And if your car is down where all the slots are filled, can you move the location of the car? No. So what happens here is that there's no action. The electrons are all just stuck. And the loud states, again, is just a grid of electron states like this. Those are like the parking spots at Logan. And you have one electron for each 2 pi over L squared space, K space. And so these are all filled, and so there's no action at all. And so in terms of motion, the inside looks like a vacuum. There's just nothing. Okay, so the nice thing is that's easy because it gives you a zero. Nothing. The only place anything can move is right around the Fermi surface, where you have states that are filled right next to states with the same energy that are empty. And in that case, you can have an electron that will move when you put the force on it over a little bit, accelerate a bit, and then carries through. And so all of the motion happens right at the Fermi surface, but not anywhere else. So is everybody? But that's a great simplification because you ask what's the energy, what's the Fermi energy, what's the momentum? It's the Fermi momentum. And then if I'm looking at a current, where would you? Let me ask you a question then. So if we, let me give you what happens to this. Now we can ask question. So suppose that we then put here's the original here, and we apply a force that's pushing the electron to accelerate this direction. It turns out what happens is the whole disk stays being a disk, but it moves over by amount P, which is just the mass times the drift velocity. That. So the whole sphere just moves sideways. And so if you look at the current that you get, J, it's just equal to the total number N times the charge times the drift velocity. But what you get is the total number of electrons times the charge times the drift velocity of one electron at the Fermi surface. The thing that's remarkable is it looks like they're just free electrons. There's only one electron. And they just add them up. But in fact, it's a degenerate electron gas. So does everybody? Yeah.
Oh, it's like, how did, like, is this shift like correlated to like a shift in the band structure, or it's like we're just saying that we're occupying a different state?
Yes.
Oh, okay.
So what happens is, let me go over here, keep drawing a place. Suppose that you start out with no force, and so there's no motion because it's equally spaced in all directions. But when you apply a force in this direction, what will happen is you'll take an electron here and then accelerate it in that amount, and it'll go an increased path where it hits the third. And then it'll get accelerated to the drift velocity. That's the drift. And likewise, you'll have one will go over here, and so on and so forth. These will go over here. And what will happen is it will start emptying out. So, other side. By having the motion on the surface, what you'll do is fill up the states that were originally empty here, and you'll empty out the states that were originally. And the one inside they're not. Yeah.
I think I actually have a question about, I get on the right, on like if we're thinking of on the right side that these electrons at the surface are able to move into a K state that's empty.
Right.
Because there's no barrier to that, like they're not
Right.
blocked or anything. But on the left side, if there's no shift in the center, what spaces are those moving into? Like, I guess how are spaces
A
created?
good question. What happens is, when you take an electron that goes over here, you create what's called a hole. This is an electron. We use the same words in the semiconductor when you have the valence band. And you excite an electron. These provide a hole to an empty state. And then what happens is an electron over here gets excited to move into that hole.
So there's kind of like a ripple effect.
Yeah, and so the hole that one that comes from another electron can move into that hole. And so it's being emptied out on one side, and there's the electrons will pop because they're all being pushed. And so electron in here, if you put a hole here, and then you have an electron here that's being pushed, it's got a space to go to.
So would it be correct to say that the kind of electrons in the states in the center do move, but it's important to specify that it's a reaction to the states on the surface.
Gotta have an empty spot. So this is, I do a lot of stuff at the airport. I used to get conscious. And so if you want to move your car and you see that some guy 10 squirt things down just took off, you eyeball that, you get in your car and you move into that slot. Then you just moved over. It's just like that.
Okay.
If you use the lingo, you say that the holes move in the opposite direction of the electrons, and so they're all moving this direction. Too much lingo. Okay. All right, good. Well, let me get back to this and we'll try to go back to it. I'm just trying to, what we want is sort of from electrical engineering, one sort of a device model of a quantum device that is sort of a very simple model, but it gives you what you need in order to do that. Okay, and so let me get back to this. And this gives a picture. I'll sit down again so we actually record this, of how the electrostatics works. And there's a picture on the top that's sort of to scale, where you have a conducting AFM tip, which is gray, and then there's a vacuum, which is white, and then it's gas gallium arsenide heterostructure, and two-dimensional electron gas is 500 angstroms below the surface. It's that distance d. And so this is the problem you see in your EE or in your E&M course, is you have a conducting plane and you put a positive charge over the top. And so what's the image charge for a positive charge over the top of the conducting plane? Negative charge is the same distance underneath. And so that's the solution. We just say that the end of this tip looks like a point charge. And if you do that, then you get that the induced charge in the 2-dig, electric field's coming down, and it's perpendicular at the 2-dig and changes the density, is just the red curve. And if you actually do the integrals and do it accurately, then you get the black tip, black curve, which is essentially the same, so who cares? So that simple model of just having a positive charge, it knocks the electrons away, or pulling them up in this case, right underneath it. And so we use that then to actually punch a hole in the 2-dig right where the tip is. And that hole will reflect whatever's coming in. But the beauty of it is you can move the hole wherever you want with the tip. Make sense? Yeah. And oops. And so let me show again how this works then. And here we're going to be doing some of this ray tracing. And the ray tracing is, in all of these ray tracing, we're assuming that the wavelength is a lot shorter than the size of the image. So it's not like finding a hydrogen wave function anywhere. And in this case, the wavelength is about the spacing of these dashes. But then here's the electron gas beneath the tip, and you see it goes to 0 because you completed it. And this is the point contact, the narrow here. And this is looking at 3 rays that are coming out of the point contact. And so question first, if all of the current through the point contact is going in these 3 rays, and I put my tip here, does the conductance of that device change or not? No, yeah, because none of these rays hit the tip, so it doesn't matter, everything just flowing past it. But then when you move it down here, this is a little bit more subtle. Suppose that they now hit the tip on the bottom side, and there are 2 contacts. One is to the left, far away. One is to the right, far away. And if you knock the 3 rays, so they all go down, does that change the conductance? No. So it's right again, because these all stay on the same side. They're all stay on the right side, so there's no change. All the charges still in this spot, the other. But what happens here when you go right in the middle So it hits square and reflects straight backward through the point contact. Does that change the conductance? Yeah, because now it's going from the right to the left. We're trying to push it from the left to the right, but this one's going the wrong way. And so when that happens, then the conductance actually changes. And that's the signal that we actually measure when you're doing the experiment. Yeah.
Don't you have a bit of a problem where you're changing what it is you're measuring while you're measuring it?
Keep talking.
It just seems like you have this thing that you're trying to measure, and then in trying to measure it, you've like stuck yourself in the middle, and now as you're measuring it, you're changing it.
Yeah. You're getting into the problem which delayed us for a year.
Okay.
But in this, the advantage here, it's a one hit. You know what I mean? Like it hits the tip once and then it's gone. Life is good. If what we did originally, which was a dumb idea, but that's the way science occurs, is we had a device that was a resonator, which would point like this, but then we had another gate that was shaped like this. So the electrons were coming into this, but the resonator was reflecting them backward like that, so that it would make a resonant cavity. And if you change the density, this thing would oscillate as the number of wavelengths. But the problem is when you put a tip in the middle of this, okay, no good, because just what you're talking about happens. You kill the ability of this thing to be a resonator, and that depends on where you put the tip. And the images look like the instrument was broken. Great anguish, you know. Old Mark was sort of emotional guy because also he would never register for the next term, and then they would send him a letter saying he could no longer show up for work. His salary would be cut to zero, and then come with tears in his eyes. Yeah, and he said, don't just pay the money. Good. But it didn't work for a long time because we were trying to do a dumb experiment. And I said, get rid of the reflector, see what we see, and then immediately it won't work.
But once you put it in though, your wave function is different. Right? Like once you
Well, here, the wave function, let me go backwards and show you what it is. Well, actually, this is a real image. The spacing here is standing wave spacing, which is half the wavelength. And you can see it, but it's a lot shorter than the size scale that we're looking at. So it's a good model to say that they're traveling along some path and winding up a wave function, but it's not like you're going inside of an atom. And that allows you to. But part of this, originally, we didn't get your question. We didn't answer that correctly. Took about a year to figure out how. Any other questions? So to do this then, this showed the first experiment. And this thing literally, it's a lot of things are like that. You'll have a graduate student, just like Mark was excellent. All graduate students like Mark, like be good. But we're doing something that hadn't been done before. We didn't actually know how to do it. And then you have to find your way. And at some point, you get the gold ring and it works. And over the weekend, just like that, it was like a week after making it sound. And so what we were able to do is shown here. Here's a picture of the conductance of a point contact as you change the width of the point contact by changing the gate voltage. And this is 2e squared over h. This is the Landauer conductance for 2 spins up down. And it shows a nice quantization that was discovered by the Dutch earlier on, about 12 years earlier. But at the same time, we were able to image the actual flow of electrons at those steps. And in the first step here, this is the image of what's happening. There's only one mode is occupied. And then the mode for that is just a single lobe, as shown here. The picture in the center is from Rick Heller, is a picture of what the electron flow looks like inside for that subband. And on the outside is the flow that we measure using this technique by scattering. And you can see that they agree quite well. It's actually not a fit. It's just a straight do it experiment in theory. And this is 200 nanometers size. And you can see that there's one lobe coming out. You could think of this as like a radar antenna, if you know about radar, that's sending one lobe out looking for the Russian bombers who will soon be coming. I guess we think they're longer. Maybe we're friends with Russia. That's luckily. But there's one lobe. And the interference here comes from going from the point contact to the tip and then straight back. So you have a standing. And so you can actually measure the local density by looking at what that is. When you go to the second step, that means you have a mode here that has a half wavelength wide, and then a mode that has a node in the middle that's one wavelength wide inside the point contact. And there's the node. This is one wavelength. And then it has two lobes that come on the outside because there's a zero in between, and then two come out left and right, or up and down. Make sense? And so it shows that because it only hits once, and your point about if it hits many times, then this works. And if you go up to the third step, then you get a wavelength and a half inside. So there's a half, one, and then you get two zeros and three lobes. And then that also worked. And so this came after a year of everything looking like oatmeal thrown against a wall, which is not quite this. It was a different kind of art, Pollock or something like that. And so we were sort of immediately very happy because we all understood what was. And so we got this published quickly, actually, in Science, because everyone could see what. But any questions? Well, yeah.
You speak to the fringes demonstrate coherence.
Yeah. So go over here. We didn't expect to see that. I mean, it's good to not hope for too much. Better to be surprised. You have sort of a dark view of what's going to happen, and you get lightened up. But I was actually, let me use the diagram that I was showing you. It's better drawn. So if you're in a case where you're actually getting a signal, that means that you're sending some electrons along what you call a time reverse path. It's going out, straight back. And it'll bounce a bit here too, so that you're actually forming a standing wave where you have electrons going in both directions between two walls. And so when you do that, and the wavelength is set, so whether you have integer number of half wavelengths, or as I guess we're adding quarter wavelengths, it'll oscillate from constructive interference to destructive interference. And that's where the fringe is. It's kind of an interesting probe because it's actually telling you what the density is exactly where the tip is. And so if you wanted to actually image what the density profile inside two-dimensional electron gas, you could do it that way just by measuring the local wavelength. That's what I like about the imaging is you can kind of, you immediately see what you get. Make sense? Yeah.
If the electrons like are redirected into the gate, are they also reflected and that's why the electrons don't?
Oh, you mean if you hit here, it goes
Yeah.
up. Yeah, the magic divider is right in the middle. And no matter what happens, if the electron scatters and stays on this side, it doesn't change the conductance. But if it goes back and it comes from left to right and then ends back on the left, it'll change the conductance. You're just counting the number of electrons that go left to right. That's
So it would be reflected on that if it were to hit the, not the.
yeah, if they hit the this is all completed underneath, so hit where the gate is, they go off this direction. Okay. And so it also means that the reflection the accuracy that you get is much bigger, it's much sharper than the diameter of this divot, because you're looking for a glint, if you want, off the divot. Actually, I went to disco school in 1978. It was the biggest thing in Berkeley for some reason. Actually, the kids who were this tall really liked disco. The older people didn't really like it. But they used to have the disco sphere. This, see it on TV with all little mirrors on it. And if you shine a flashlight, you'll see a glint where it's just coming in square and then comes straight back, and the rest of it is gone. Or if you're military, if you want to see the Russian bomber come in and you're shining radar on it, you'll get a glint when it hits square. Okay, well, let me show you. Well, it's good to have a lot of questions. One of the things it would be good to get is kind of a simple device model of a quantum device that has electron waves traveling around inside it, so that you can get an answer without doing any integrals, is what you want. It turns out the devices are dirty and misshapen enough that doing these fancy integrals won't you get the right answer anyway. So it's just as well to use a pencil and then measure it. You're in good shape. But let me show you something else. And then this is literally 2 weeks later. And when we were doing the experiments, this is, instead of being a half a micron here, we're just looking there, we just zoomed back. And literally, we hadn't done this before because we were going for the big win, so we wanted to go sharp in and see the codes. And then we were happy because we saw them. And then we zoomed back, so this is what, 5 microns. And then did the same experiment, same temperature. And then we saw this. And we were depressed. Okay. It's Mark and me, and we said, well, the instrument's not working anymore because it was all homemade. And the trouble is, you make it yourself, you don't know. Like, I like to cook, but usually the first time I make it, people think it's good, and so you have to do it like 3 times before you get into it. And then we looked at this and we said, wow, we were lucky, and I guess one good luck is enough. We're done. But then we had lunch with Rick Heller, and then he immediately was excited about it. And he said, well, this is what you should see, or some golden words like that. And so I'll tell you that story. But what we saw, instead of seeing sort of broad lobes, that would sort of be big and then fill up the space, we saw these very narrow branches that are narrow, and they're very persistent. Once you form it, it doesn't go away. And then it doesn't get wider either. But from one sample to the next, the branches are not in the same place. You could redo the experiment, the branch on that day will look the same over and over again. But you warm it up, cool it down. It seems bad. But you can see that it's coherent because there's these fringes everywhere. And if you look at it, there's with some experience, there's a lot of V-shaped structures in this, and there's like a V there, there's a V there, V there, V there, so on and so forth. And so all of these kind of V's stack up one after the other. And you were talking about Michael Berry and Rick Keller, and what they both have been worrying about for about 10 years was there's something that's called a chaotic stadium. It looks like this. And then if you have electrons bouncing around inside classically, they'll have chaotic orbits that don't reproduce, or in some case, some periodic orbits, which we just go like this between sides. And people wanted to understand how this worked. And the classical version goes back to Poincaré and whatever it was. But they wanted to do the quantum version of that. And it's something that Rick was involved with. And this is sort of related. It's a lot easier because there's nothing reflected waves. And so how would that happen? This is just showing you that it really occurs. These are the modal patterns. There's the first mode, that is when contact is a half a wavelength wide. Instead of just getting one lobe, you get these straggling things. The second mode, where there's supposed to be two, but then it gets a bit broader, but they're still sharp. The third mode, where it's supposed to be three, but then it's sharp again. Fourth mode, so on and so forth. And they reproduce on one day, they reproduce very accurately. And I should say the signal to noise on these is very fast. It only took a couple of minutes to make one of these scans. And so where does that come from? And yeah, so this is things that I was answering questions last time about what sort of makes the electrons scatter in this system. And the way it works, and this was actually made by Rick Keller, a good art, good to work with if you're making papers. But here's the gallium arsenide. Here's Al gas, and it's actually doped by a layer of silicon. And the electrons fall off the silicon and into the two-dimensional electron gas. But it leaves behind these ions, which are the red ones. And so the ion depletes the electrons below it. It's a positive charge. It puts a bump in the electron gas. And so it creates a potential that the electrons are moving through that has mountains, valleys, that sort of. And this is a standard thing that happens in semiconductor devices. You have to dope it somehow. And one of the dopant ions then cause trouble because they'll scatter. But then what Rick did is he knew already the way this worked, but there's a model right here where you're doing ray tracing again. We have a bunch of electron rays that are coming from the lab that are all parallel, and everything is just going in a straight line. And then you put a positive charge above it here. This would be like, positive charge has a negative charge. I mean, the same kind of logic. And so what that does is change the density here. It's like changing the index of refraction if we're thinking about optics. And it makes a lens. And so it bends the rays over like that. And it's actually real simulations. Hard. But what happens, it'll actually bend them down to a focal point. And then after that, the focal point, it actually goes over, as shown here, it makes this V-shaped structure. And it turns out that the shape of that is just as if you had taken a piece of paper put rays on it, and then rolled it around in a cone. Okay, mathematically. And what happens with the cone is there's the cone of your paper is coming around like that, is when the cone is perpendicular to you, you get two spikes in the density of flow that come with the two rays. And that's the origin of how this works. The technique, this type of scattering is called small angle scattering, and it's no, it's a semiconductor. You'll know that, but they didn't realize that this is kind of flow that they thought before this. They thought that that was just totally random, with no shape to it. But in fact, that's far from the truth. It actually has these very sharp branches. And if you do a simulation in small angle scattering, in theory, you get a picture that looks like the one on the right. This is your part again, where the bumps, the mountains, act like a lens, and they create these V shapes, like you're seeing here. And then once the edges of the V are formed, then they're very robust. They don't like to go away anymore. They will sort of amplify themselves because that's where all the electrons are flowing, and then they'll create more V's. The same angle. And before this, people didn't understand that that's the way it works. But do people see where this comes from? But it's all, this is the basic origin of it. And they tried to do sort of a mathematical, Scott Shaw, working with Rick, was trying to do like a scattering transport model with this, but the math was like too hard. You can do it artistically and you can see what the effect is, but to actually do the integrals and all that, they weren't able to. It gets it's things that are in topological science, these things called vector bundles and all of that, and fancy quantum materials. This kind of mathematics is something that's currently people are trying to. And so here's another picture of showing the same thing from Rick Heller. And it shows the electron flux and simulations on the top, and on the bottom shows the mountain range that it's flowing over. And then they put a shadow. This nice, working with him was wonderful, because if I had to do this, I would commit suicide and make it work. But they actually create a shadow to show where the electrons are actually traveling mountain range. Yeah. So this turns out in the two-dimensional electron gas, this was not the way that people were thinking about it. They thought it was just totally random. Whereas in the non-uniformity is high, it's really going from 0 to a lot and not very large distance. And so Rick is enjoying himself sailing. He's probably asleep. I think it's probably like 4 in the morning or something like that. But it turns out in the ocean, you see something that's quite similar. There's actually the distance that sound can travel in sound channels is all the way around the world. So you can have a storm or even hooting whales in the Indian Ocean, and you can actually hear it in California. And so people have done experiments where they look at some event that occurs a long way away in the ocean. And it turns out that the bottom, of course, is not flat. And if you look at the sound propagation, it also generates these branches that have the same form as this. And even in the cosmos, there's gravity can actually bend light waves. And so something very heavy essentially makes a lens. And you can also, Rick did some work with some cosmologists showing that for light traveling through the universe, you also get this kind of effect. That's one of these things that, again, is sort of artistic, because the theory of doing this the written out theory is too hard for people. But on a computer, you can actually do simulations. And you get structures that you can see that are very recognizable, robust, and happen every time. So it's a bit like engineering. Any question?
You talked about sort of heating up and then cooling down, and each time you do it, it's a little bit different.
Yeah.
Can you speak to like specifically what's going on that's causing it? Like when you heat it up and cool it down, what is changing?
Oh, sure. Well, there's a lot of silicon atoms at random locations like that. And when you heat it up, then they all ionize. When they cool it down, some of them will be ionized, plus, and some won't. Another one over here would be plus. And which ones turn out to be ionized for the electrons? Each time you cool it down, it's just random and out of control. But the pattern will be different. If you keep it cold, then it'll.
What temperature was it at?
These are all at 4 degrees. The experiment, actually, the signal is big. It's like a 1% signal, not small. And we did it DC, you just put a DC current through it. And you could actually take an image like that. So it's sort of fun once it's working. Like, suffering. There's a famous Erwin Hahn, when I was your age, I was looking who to work with. He's famous in NMR. And really a nice guy. This is the guy, and he showed me the apparatus to do some double resonance. That is, you have a resonance, then you resonate that. And you know how long it took to get 1 point on the curve? 2 weeks. And I just think it's supposed to. I just looked at it. I was gone. I can't do that. You have to meditate, or I don't know how you make yourself okay. So, but he's a wonderful guy, really. Well, let me show you some other things which are like, here's a picture, and I used to have this. And this made the cover of Nature. I think they liked biology a lot, and they thought it was sort of biologically. If your bathroom, you don't clean it often enough, you get something that looks like this. But it's not, it just has a point contact. It's right at the center. And then it's just flowing out with a small angle scattering. And you can see eventually it gets kind of random, but it's more branchy than random, which is kind of interesting. So if you're making a device that's, not enormous, you really care where those branches are. And so that's something that people have to sort of live with. And there's Nature. But that all happened inside 2 weeks. So we got both the Science and the Nature paper and the cover. And at that point, that was too much. But then for Mark, and then when he was looking for a job, then everybody offered him a job too as a postdoc, which again, he's such a nice guy, it was like too much. I said, look, Mark, you're worth it. But it turned out well. And the NSF liked it too, so we're in good shape. Well, let me show you the interferometer. We did an imaging version of this. And this was done by Brian Leroy. He's a professor now at the University of Arizona. And this, we wanted to actually do the interferometer on purpose and show that it works. And so we made a QPC like that. And then we put in a reflector, which actually curved and is designed to reflect the waves directly back to the QPC. So we're making a resonator that'll have standing waves. And then to do the experiment, we picked a similar place to put the tip, and the tip is a reflector too. but it's not focusing. It's just a time reverse pad. And then the idea that we would have sort of a 2-point interferometer, one with a path that's going to the reflector, and the other one that's going down to where the tip was. And then we could measure the electron wavelengths just by scanning in an area down there. And so it worked. You can understand it just by drawing some rays that are winding up a phasal ray. And this is 100 nanometers. And as you turn the reflector voltage on, reflector gate, you start out with not a very large signal. But when you turn the reflector gate up to reflect electron waves back, then you turn on a very nice standing wave. And so that shows how that you can actually, so the demonstration is if you wanted to make a device that actually works on wave reflection, as opposed to counting electrons, you're going to look at electron waves and make interferometers out of it, but you can do that too. And of course, if you know about photonics, the things people do, like Marco Lanchar and other people, they do a lot with wave reflection of light and make Mach-Zehnder interferometers, all of these fiber optics. Yeah.
Would there be much difference if they were both the current reflectors and they're 2.5 factors?
Oh, 2 of them? Yeah, you would get a much stronger signal. Yeah. Because here, when we're scattering here, that it goes off in all directions. But the bad part of it is that nothing's perfect. And then if you had 2 of these, then proving that it's, you have to go against the oatmeal is your enemy kind of thing, and proving that it's actually real is a bit tougher. But that would work. And you can make a Mach-Zehnder interferometer for electron waves. Somebody must have done that. That's where you have 2 paths like this, and then you change the phase one path by putting the voltage on optical material. But all of that is possible in terms of things that people are actually using it for, not so much. But it's totally.
Is it just that light is easier to, we're better at measuring and moving and whatever, like that's why people are doing it with.
Yeah, sure. Well, light is it's has the advantage that they're bosons, right? So that means that fermions, you can only put 1 fermion in each state, and so you can't make it too coherent if you like. Whereas photons, you can put as many photons as you want in exactly the same state. And so that's why a laser works so well. If you load them up, then you can get tons of photons, and it actually goes classical, and you can have a laser say what the electric field value is. And so with photons, it's very good to do. You can think of it as being quantum mechanical, even when it's classical. That is, when you're not counting photons, but you can use the wave aspect of it very easily. And so people like it. Let me just wrap things up. What else? Oh yeah, double. Well, this was just showing off, but it's sort of at the fringes of working. But here's a single bounce interferometer, but you can also see a double bounce interferometer where you have 2 bounces with reflector, and then you put this twice as far away, but it takes twice as long to get there, and you can still see the fringes showing up twice the distance. And it's just demonstrating that you can start doing this phase electronics using electron. And here I'll just show this one, and then we'll finish. And so this is a nice picture of Kathy next to Sheen, and she has the very much Kathy look, like she might kill me if she doesn't. I mean, there's this edge. But she's fantastic. She built this experiment, and then she got the whole thing to work, which was really not trivial. this is inside the tour. It's business cards, which is holding right here. And there's something that was discovered actually by some heroes in Holland in about 1962 or 1963. That's called magnetic focusing. And they actually did it in the metal with metal point contacts. And it turns out that if you have a point source at one point, then you have a perpendicular magnetic field, that the electrons all go in circles. Here you have, they're coming off at different angles, but they're all in circles. And then the diameter comes down here, that they refocus at the diameter. And it's just the geometry of a circle has two vertical edges to it that are separated by the diameter. And the graphics shows the way that works. And if it bounces again, then it keeps doing that. And these are simulations. And so what she did was to actually image this in a two-dimensional electron gas using some point contacts, and then the same imaging technique that we were talking about. And, oh, will this work? That would be lovely if this worked. And so what you can do is to, whoops, I guess it doesn't work. It's a nice, oh, it looks like it should work. Go, go, go. No, that's too bad. It's actually a nice movie that shows you how the thing forms and all that. I don't get the job. But this shows what she did was to look at the scan probe microscope imaging of this magnetic focusing. And there are 2-point contacts on the X on this part. Coming at you is the signal, the change tip that's doing, and the Y direction is the other direction. Yes. And as you turn up the magnetic field, you can see the diameter, one diameter right here. You turn the field up twice, then you get a bounce right in the middle, the edge, then it's this. And by the time third, this begins to look like oatmeal at this point, but with a glass of whiskey or something, you start to see. But this is sort of the edge. So that was really impressive that she got that to work. Later on, we were actually able to measure something called Andreev scattering, where you put superconducting contacts on and then image whether it's electrons or holes. But that's probably a good place to wind up. Any last questions? But what to back up to the beginning, what I'll do is I'll put together for how do you model a simple model of a quantum device, something like this, a little bit more broadly, but it's some chamber with contacts and waves going around, where I'll put together some of the things that we had, like this ray tracing, the Landauer, how do you get that relation, and put that together and then send you a copy as sort of a to get you started on the way these different things work. The nice part of the ray tracing is you really can do it. And I can draw a Fermi distribution to a couple percent, but like this practice. So you can really do stuff quite simply once you get the picture, I believe it. And then you can also figure out how the interference. Okay, good. So Monday is a holiday, okay. And the quantum Hall things, I was talking with Jun Kai about that. Well, in the practice on Wednesday, we'll go over edge states and how that works, because understanding how the edge state gives you quantum Hall is sort of the key thing. And that's what Bert told everybody how that works. So we'll get launched into Bert algebra Friday. Good. Fine. Thanks. Chocolates, did everybody get a chocolate? Go for it now. Finish them off.
Question about my presentation.
Oh, let me just turn this off a second. No. Where is it?
So
Right there. Stop. Oh, thank you.
that's the pause, the one next to it is the stop.